On this episode of Bang Goes the Theory, Dallas meets a real live rocket man.
I like the kind of al fresco open plan design you've gone for.
I look at brain training in action.
Is there any evidence at all to prove that brain training actually makes you brainier?
And Jem crashes a helicopter.
Whoa, we've really overcooked it here, haven't we?
Welcome to Bang Goes the Theory. Now, we start off tonight's show with brain training. Chances are you or someone you know has bought a brain training game by now, and they are big business. It's estimated that the US alone spent over $90 million on them last year. But do they work? Well, we thought it would be a good idea to put them to the test. Everyone is doing it, from your gran to your favourite celebrity to your 5-year-old niece.
And the manufacturers say the games will do everything from giving your brain a simple workout to actually boosting your brain power.
But is there any evidence at all to prove that brain training actually makes you brainier?
I've invited a couple of guinea pigs to join me at Cambridge University. I'm going to set Jem and Dallas a 6-week course of brain training to see if it makes any difference to their brain functions. But first, I need to find out what shape their brains are actually in.
So, Jem, I need you to sit over there for a bit, and Dallas, you're coming with me.
What are we doing?
I'm about to set Dallas some brain training tasks. Sounds pretty simple, but the catch is he'll be inside a functional MRI scanner while he does them, and he's never been in one before.
You're getting your brain scanned. How cool is that?
I don't want my brain scanned.
This will show me exactly how hard his brain is working, but it turns out Dallas is a little bit claustrophobic.
Are you all right?
Yeah, no, it's just, I'm fine. Sorry, it's freaking me out. That's okay.
Despite his apprehension, apart from the noise and being in a small space, Dallas will experience no discomfort whatsoever. Inside the scanner, there's a computer screen and a button box to press for his answers. With the help of neuroscientist Dr. Adrian Owen, I'm going to see Dallas's brain in action. This is his head, and it turns out it's a big one. No surprise there, then.
But does a big head or a big brain mean that you're more clever, Adrian?
Well, Dallas's head is big, but his brain isn't particularly big, I have to say.
Right.
And really, there is no evidence that having a big brain doesn't necessarily mean you're any smarter.
OK, Dallas, here comes the first brain test. Good luck.
The first test is called visual search. Dallas has to decide if 2 images are the same or different. It should tell us how good he is at doing things like finding keys in a drawer of junk in real life.
Look at that, that's amazing.
The back of the brain is really starting to activate. What's happening is the parts of the brain that are working hardest are requiring more energy to do that, and they're drawing more oxygen to replenish lost energy.
So, Adrian, I'm a little bit confused about these brain training games. I mean, isn't it true that if you repeated one particular game again and again, you would just get better at it based on practice, right?
Well, the idea of brain training is that it gives your brain a full workout. We don't know that that's the case. We don't know that people's brains are actually going to improve in any measurable way.
Oh, you just got one wrong. You're getting a lot of rights, though.
The second test is a reasoning test. This looks at how good you are at logical thinking and problem solving. For example, planning what time you need to leave home to catch a train.
And what part of the brain usually fires up most for this kind of activity?
Actually, in Dallas's case, we're getting much more frontal lobe activity than we've seen previously. I think this is really exercising his problem-solving abilities.
Okay.
And now for my second guinea pig. Jem will be doing exactly the same tests, and we may well see some differences in his visual search and reasoning skills.
Are you okay? All right, this is it. Are you nervous?
I am a bit now.
First up, the test to see how good Jem is at finding objects.
Are you ready? Are you concentrating?
All right, he's off. Back of the brain.
Oh, definitely. He's doing all right, isn't he?
I think he's getting a bit competitive here.
Of course he is. They're two blokes.
And finally, the reasoning test to see whether Jem is a logical thinker.
Just from knowing them, I would have thought actually that Jem would be better at problem solving because that's all he does. He's always building things as an engineer.
It'll be very interesting to analyse the brain imaging data, but also their performance in order to see whether it really does seem to correlate with what you know about them.
So, do their brains work differently given different tasks? And more importantly, could brain training change that over time?
He's still alive.
How was it?
So relaxing.
Yeah.
Well, I'm going to leave you both to recover, and me and Adrian are going to analyse the data.
I'm a bit nervous about these results.
Are you? I'm nervous in that they're going to come out and say, I think you're on borrowed time. The way your brain's not functioning, mate, you'd be lucky to make it home.
Do you think our brains are wired differently?
Yeah.
I think they might be.
So do you want to know the results?
Maybe you should put us out of our misery.
Don't be so enthusiastic. Okay, Adrian, take it away.
Okay, on the first test, the visual search task, Dallas, you did better. The one that required logical thinking, Jem, you were way better than Dallas was.
That's like probably because it's my job.
Fair enough. So what does that tell us about our two boyos?
Well, to be honest, if I had to be good at just one of these tasks, I would choose the reasoning test.
Sorry, Dallas.
Oh no, I'm so upset. Is there any way that I can improve on it?
Well, this is great because it gives us something to work with. So we've designed some brain training tests for you. What I want you to do is to try them at least 3 times a week for the next 6 weeks.
Okay.
And then we're going to see whether it improves your brain function. Okay?
Okay,
Okay.
I'm game if you are.
I figure we're both mature enough not to turn this into a competition.
I'm nervous.
Oh, don't be nervous, Dallas.
How could I not be nervous?
Well, before I tell you the
just
results...
tell us the results.
No, I want to talk first of all about your training sessions, okay?
Okay.
You were both supposed to do 18 sessions. Right, Jem, you did about 23, which isn't too
Oh, did I?
shabby.
Good.
Yeah,
Not
not too
bad.
shabby. And, you know, it shows sort of like suitable enthusiasm. Dallas, you did 48 sessions.
I actually got completely obsessed by it.
You
I became a
did?
man possessed.
You were
by
totally freaked out by the initial results that you
That's
worked
immense.
every minute of every second you had free, clearly. That's bordering on cheating.
I was crushed by his comments, you know
I
what I mean?
know.
And I'm
We
also
noticed.
childly competitive with Jem.
There was supposed to be no competition, but anyway, there clearly was. This is your spatial awareness before result. Now, we kind of saw that you were quite good at those to start off with, okay? Now, after 48 sessions of training, here's your after. Absolutely no difference
Wow.
whatsoever.
Exactly the same.
With all the training you did, no difference.
I'm surprised about that because, I mean, that was kind of my favourite one. And
I
I'd
know.
sit there for hours.
I know.
At night, locked up.
The thing you've got to remember is you were actually very good at it to start with, unlike your verbal reasoning tests. Do you remember those?
Oh, I hate verbal
The ones that
reasoning.
haunted you at night. Okay, so remember this was your
Oh, that's
before.
embarrassing.
Okay, it's not too bad. Are you ready for your result?
Okay.
This is it after your training. Massive improvement!
Oh
Dallas
my,
Campbell.
that is a
That's
big
really good.
improvement.
Yeah. Well done. I mean, that obviously shows that something's going on in your brain. But yeah, we have to remember, obviously, that this is just, it could be just anecdotal because it's just 2 individuals doing this test. But it's a good positive indication, all right? Now, Jem, are you ready? Okay, let's start with your reasoning. We knew he was a good problem solver. That's what he does for a job,
That's more than where I ended up.
But
Yeah.
it's very close. Anyway, now after your 23 sessions of practice,
Wow.
a little improvement.
Yeah.
But, you know, you're up there anyway,
I'm
so
happy
that's
enough.
pretty good. All right, now, for your spatial awareness test, which you weren't quite as good at, all right? But after training, so again, a little bit of an improvement, not bad
And
going
does that
at
help
all.
table tennis in any way? No.
Well, yeah, at least you know where the ball's supposed to go.
Good.
But no, well done to the two of you.
Thank
That
you.
was really good.
Okay, next up, it's space, and it's a big personal obsession of mine. So I went deep into the Mojave Desert to meet a real-life rocket man. Getting into space used to be something governments spent billions on, but now a few rich entrepreneurs are trying to do it for just a few million. And if they get it right, they'll get an awful lot richer. This corner of the American desert has always been about pioneers. It's been about real heroes. It's been about constantly pushing the envelope. In fact, literally just a few miles down the road there at Edwards Air Force Base, Chuck Yeager became the first person to break the sound barrier. And what's really interesting is that the experimental aerospace tradition is still carrying on right now, but not by government agencies, by a handful of, albeit extremely wealthy entrepreneurs who all share that deep passion for adventure. One of the great advantages those new space pioneers have is that NASA has done the groundwork. All men like Dave Maston have to do is build on their pioneering programs.
Yeah, we're trying to basically drop the price of getting a payload into space by an order of magnitude.
So how much cheaper do you think you're going to be in the long run?
So, in the long run, I think we're going to be hundreds of dollars a pound instead of thousands of dollars a pound for a payload to space.
Wow, that's a huge difference.
Yes.
Yeah. Forecasters reckon that $178 billion will be spent on launching satellites over the next 10 years. And beating the opposition on price is where minnows like Dave Maston expect to make their killing.
Can we do the two hardest parts of a flight? Take off and land.
Okay.
If we master this, we get this really good and we're very happy with it, then we'll take it to the next level and start delivering payloads into space.
It's a bit smaller than I imagined, but I love it all the same. I like the kind of al fresco open plan design you've gone for. So does this run on sort of regular unleaded, or what kind of fuel are you
actually,
using?
it's alcohol.
Oh, it's alcohol?
Fuel. It's a wonderful fuel. It's very green.
So you've got alcohol up here, and then in here...
It's liquid oxygen.
Oh, that's oxygen in there. But what are these big tanks on the side?
These are our pressure tanks. What it does is it drives the gas into the rocket engine.
So it's not just gravity letting the fuel drip down, you've actually got gas that's pushing
we're actually
the fuel
forcing
in.
the fuel in.
And this is one of the key innovations of Maston's rocket. The most important aspect of any liquid rocket system is getting the right fuel mix into the combustion chambers. Older rockets made by NASA used incredibly complex turbopumps which added a lot of weight. Maston's rocket, called the Zombie, uses only compressed gas.
In order to overcome all that gravity to get that 100 kilometers or whatever, we have to carry lots of propellant.
Okay.
And all of that propellant is on board.
So that's more weight.
So that's more weight when you start off.
Okay. Getting a rocket to leave the ground in a controlled manner when it's carrying its full fuel load is the key to a successful launch. And that's what today's test is going to be all about.
So you end up with this huge vehicle with all this propellant to lift a very small payload.
Okay. So presumably as it goes higher and higher and higher, it's getting lighter and lighter and lighter.
And easier and faster accelerations,
Okay.
yes.
But does it work? This is one of the maiden flights of this pioneering rocket system.
Start prime.
With about 130 litres of incredibly flammable propellant, one mistake could be costly. Dave has a right to be worried.
I'm nervous. Just it'll do something not quite right.
Okay, go to engine start.
Okay, fingers and ears.
Firing in 5, 4, 3, 2, 1, fire.
Now, you might not be too impressed by what you're watching, but taking off and hovering over a stream of hypersonic gas is an incredible feat of engineering, one that bodes well for the next phase of development. Well done. Congratulations.
Thank you.
Very good, very good. Okay, but bottom line, how long before you actually go into space, do you think?
At least 2 years.
2 years. That's
About 2 years.
2 years is good. I mean, I can wait for 2 years. It might be hard to believe, but if Dave Maston does get into space, this corner of the American desert could soon look like Cape Canaveral.
Great stuff there. But you know, I'm imagining space gridlock up there with everybody's DIY space travel kit.
I know, but it's exciting because suddenly space is becoming for the masses. You know, it's
Yeah.
being taken out of the government agencies' hands. It's great.
Do you know what I love, though? The shape of that rocket exhaust.
Oh.
I mean, wasn't it magnificent?
As an engineer, you would have loved it out there. You'd have loved it.
I'm sat here very jealous.
Be jealous. Be very jealous.
The problem your man Dave Maston's going to have when he launches that rocket, though, is trying to avoid space junk.
Oh,
Yeah, there's
absolutely.
lots of
Yeah.
it out there. NASA reckon there's about 600,000 pieces measuring a centimetre or more flying around up there. And it's all from dead satellites, from rocket launches, all that kind of stuff.
I mean, those are the relatively big bits. I mean, have a look at this. This is actually a bit of a bumper shield from a satellite that's been hit by something. And that hole was made by a tiny, tiny little ball bearing, about 0.8 of a millimetre. It just goes to show the damage that can be done by even the smallest bits of debris. I mean, this is less than a millimetre. I mean,
That's
this is absolutely... I
minuscule.
mean, you can't even see it. It's amazing,
And he went
isn't it?
straight through it.
Straight through that, absolutely.
Amazing.
Yeah, but it's because of the speeds things are travelling up there. In order for something to be in orbit, it has to be going fast enough to avoid being pulled back down by Earth's gravity. And that's a phenomenal velocity. Say, for example, the space station, which is 400 kilometres up. That needs to go at 7.5 kilometres a second. That's 17,000 miles an hour. I mean, they're speeds that make bullets look like tortoises.
And because the energy with which something hits something else is related to its speed as well as its mass, if even the tiniest speck of paint hits something while it's travelling at 17,000 miles per hour, it's going to cause some serious damage.
And to make the problem even worse is that most of that stuff is just stuck there.
No, exactly, because as you go outside the Earth's atmosphere, there are fewer and fewer air molecules. And for a flying object, it's collisions with air molecules that slow it down, like air friction. No air molecules, no reduction in speed.
Exactly, and if it's not slowing down, it's not going to drop out of orbit, which means it's going to just stay there. You know what we need is some kind of like giant space vacuum cleaner or something.
Yeah, Dallas, a vacuum cleaner in a vacuum.
Yeah. How would that work exactly, Dallas?
Touché.
Actually, that does sound like a question for Dr. Jan. Speaking of which, our resident brain box is out and about this week, messing with microwaves.
Microwave ovens. We've all got one in our kitchens, and I'm going to show you how they work. And what I'm going to use is a piece of broken glass and a blowtorch. This bottle has been in the microwave almost 10 minutes, and it's still not really hot. Slightly warm, but not hot. It's just like the glass plate at the bottom of your microwave doesn't get hot either. But also in the microwave, I've put a jar of water. This definitely is hot. You can see it steaming. So what's going on here? How come some things get hot and some not? Well, microwaves in these ovens work by making molecules in stuff wiggle like that. And as they wiggle, they bump into one another, and that heats them up. The molecules in this glass can't wiggle very much at all because they're held firmly in place. And so that means they don't really heat up in a microwave. But if I melt glass, yeah, make it a bit liquid, then suddenly it allows the molecules to wiggle, okay? That's where the blowtorch comes in. So if I heat up a piece of glass till it's, say, red hot, and just put it in the top of the bottle, then hopefully the microwaves will be able to get to work on the glass, and then they'll melt the rest of the bottle as well. So actually this is the same reason why it's quite hard to defrost things in your microwave, because if you look at ice, it's very solid and the molecules can't wiggle very much. I reckon that's almost getting there. 3, 2, 1, go. There you go. And if you look right at the top,
oh, right, yes, you can see that.
The little bit of glowing glass that I put in has now heated up the rest of the glass molecules in the bottle and allowed them to wiggle too. And so they're melting. The whole bottle is just disintegrating before our eyes. It's really cool. Whee! So a bit's fallen off the bottom into there. It should carry on going. It's quite pretty though, isn't it?
Yeah. Are you going to take it out?
I will take it out of there so that it doesn't burn a hole in the bottom of my microwave.
Does it affect the guarantee of the microwave for melting bottles?
You probably shouldn't do this at home. You might wreck your microwave, and you probably shouldn't be messing around with blowtorches.
You might remember this.
That's right, Liz had a bit of a thrill ride in a helicopter flown by ex-world freestyle chopper pilot Quinton Smith.
It got me thinking about how helicopters actually fly. I mean, they're amazing bits of kit. You cut the power to the rotors, and it just doesn't fall out the sky.
Yeah, although it kind of feels like you are falling out of the sky, Jim.
Yeah, but not exactly. I mean, the thing just didn't tumble. As an engineer, I was amazed how stable it was.
Yeah, no, it's pretty amazing. But didn't Leonardo da Vinci invent the helicopter?
I think Leonardo da Vinci drew a kind of helicopter. I firmly believe there is no way it would have taken off, A, with the air screw, and B, it had no stability to it at all. Watch this. Liz, here's da Vinci's helicopter with the benefit of a modern motor. Let's see what happens as we go for liftoff.
Oh, that's rubbish.
And then compare it to this one.
Okay.
Modern aerofoil rotors, tail rotor for stability. 1, 2, 3. There we go.
It's just so elegant.
Now, if
isn't it?
Leonardo couldn't crack it,
Beautiful.
I thought I'd go and find out exactly how helicopters do fly.
This is the Westland Sea King Mark IV Commando helicopter. It weighs in at over 10 tonnes, has a top speed of over 140 miles an hour, and is powered by 2 Rolls-Royce turbojets driving 5 rotor blades nearly 10 metres long. But the £20 million question is, how on earth do 5 fairly flimsy blades lift 10 tonnes of Royal Navy Sea King helicopter? Now this feels wrong, like my heart's going when I do that. But the fact of the matter is, if each of these blades couldn't have 2 tonnes hanging on the end of it, it couldn't lift the helicopter. And oddly, it's the extraordinary flexibility of the blades that allows the whole thing to fly. If these were stiff as a board, there's no way that helicopter would be of any use to anybody. Now, to get a helicopter off the ground actually uses some pretty simple physics. Each rotor acts as an aerofoil, just like a normal plane wing, only this one goes round and round. To generate lift, all you need to do is pull up on a little lever called the collective, and each of those blades starts to angle up slightly at the front. This so-called angle of attack helps to suck air from above and whack it downwards. To quote old Isaac Newton, every action has an equal and opposite reaction. So if the air is being forced down, the helicopter is going to be forced up.
Now, the rotors up there going about 200 revs a minute, which actually isn't much faster than your bike wheel goes as you're going round town. But because they're each 10 metres long, the tip speed's nearly 400 miles an hour, and it creates an awful lot of downdraft. The blades bend up enormously during flight. It's known as the cone, and they do not stick out straight, they bend right up. Now, that flexibility in the blades is a very good thing for us inside here, because it gives some kind of suspension to this vehicle. I mean, they're pretty shaky things, but it kind of damps things out a little bit. Right, there's only a limited amount of time I'm prepared to stick my head out of the helicopter. I'm coming back in now. The astonishing and very concerning thing about this aircraft is those rotor blades that are responsible for keeping us up here are held on by just one nut, and I have no idea who tightened it up. I mean, I assume they were extremely good.
The pilot, Lieutenant Commander Jim Newton, is one of the best in the business with over 20 years' experience. It takes more than 100 hours to learn to fly a Sea King, so I couldn't quite believe what happened next.
And I'm still in the jump. Speed's building up, doing about 102 miles an hour. Okay, I'm going to settle the aircraft down and I'm going to hand you control, okay?
My only training was half an hour in a simulator earlier on.
So, you have control.
I have control. Thank you. I'm not touching anything because it seems to be going quite well.
Okay.
Okay.
Flying in a straight line is one thing, but to turn the helicopter, I've got to get my head around a lever called the cyclic.
I'm now going to try and fly an aircraft and talk at the same time. Now, the cyclic is so called because it shifts the pitch on things cyclically. The blades will pitch up more on the left and less on the right, for example, and so this enables me to turn one way or the other, or to go forwards and backwards.
Increasing the pitch of the blades for just one part of each revolution will generate more lift at that point, making the helicopter tilt in the opposite direction.
It's almost hard to breathe and do it at the same time, I find, let alone try and talk and do it. It's a phenomenal feeling. I've got to say, I'm almost shaking with fear after having had control of it, even though you're there. Oh.
Okay, I have control for a second. I've just got to bring it down, Jem, because we're a little bit high at the moment. Okay.
I cannot believe you got to go up in a Royal Navy helicopter. What's that about?
I told them my degree in aeronautics somehow qualified me as a pilot.
Yeah, degree in aeronautics or not, when you were practicing, you were rubbish. Have a little look at this.
We are quite high at the moment. Okay, I'll stick forward. Yeah, and that. Whoa! We've really overcooked it here, haven't we? That's too quick to descend for sure. Oh my God! Hold it Oh my life!
And on that rather non-heroic note, it is time for us to go. See ya.
Bye.
Dallas, what's he doing up there?
I've no idea. He said something about helicopters or auto-rotation or something.
what?
I don't really know. No.
Oh, wow!
Jem, you're a genius!
That was beautiful!
That's how auto-rotation works.